Let us start solving this problem by the following observations. First one, we have a square root number within a square root. Second observation, we have similar terms, namely the square root of x minus 1 in both expressions. Third observation, we have numbers like 3, 4 in one pair. Okay, I'm making pair and I will explain why. We have two numbers 3 and 4 in pair and 8 and 6 in pair. Okay, I'm assuming here, let square root of x minus 1 is equal to some number p. Please notice that p exists only if x is greater than or equal to 1. Otherwise, this one will be root over negative number, and that is not mathematically acceptable in real domain. Okay, if I know this, then I can say x minus 1 is equal to just p squared, which implies x is equal to p squared plus 1. Okay, means I have transformed one variable into another. Here I have translated x into p squared plus 1. Okay, now we have to replace x by p squared plus 1, and wherever we have root over x minus 1, we have to replace it by p. So let us replace. We get a square root of p squared plus 1 and plus 3 we had, minus 4 times of, since I have taken root over x minus 1 as p, so I will replace by p. Similarly, a square root of p squared plus 1 in the second expression plus 8 minus 6 times of p. Right? Now we come to third observation. Okay, why 3 is necessary here? Because we know that from this transformation, when we add 1 here in such a number which gives a perfect square, for example 3 plus 1 gives a perfect square number, right? Okay, similarly if I take 8 plus 1, we will obtain 9, again a perfect square number. So basically x transformed to certain positive number plus 1. Okay, and this one is necessary along with 3. This number 1 is necessary along with 8 to make it perfect square number. I hope it is clear. Okay, now what is role of this 4? So if I will consider this 4, then we will get a perfect square number here. Similarly, here 8 plus 1 9 and 6. We know that 3 plus 3 combination, that will give a perfect square number inside this root. Okay. Further, we can write simply this as p minus 2 whole square. Similarly, in this case, we will get p minus 3. Okay, which is equal to 1. Okay, now here we know that whenever we have a number a perfect square number within a square root, then it turns out to be a modulus function of x, like this. Okay. Now, using the same modulus property, we can write as p minus 2 mod plus p minus 3 mod, and sum total of course equals to, so sum of these two modulus functions is equal to 1. Suppose this p is positive, okay, and this p is negative, then positive and negative cancels out. So finally what we get? Infinite number of solutions for p, right? Similarly, if this p is positive and this p is negative, so this p and this p cancels out, again we have infinite number of solutions, right? Let's say p minus 2 is greater than or equal to 0 and p minus 3 is greater than or equal to 0. Okay, now here is the problem. If I consider p minus 2 greater than or equal to 0, that's fine, no problem. But when we take p minus 3 greater than or equal to 0, which implies that we have at least one possibility of getting left hand side 0. Why? Suppose this p minus 2 is 0 according to this OR condition, so this will be 0, and suppose in this case as well we have 0, so this will be 0, and 0 plus 0 is equal to 1, which is in contradiction with basic mathematics, right? So what we will do, we will remove this equality from anyone. I can remove either this one, leave this as unaffected, or put equality sign here, or remove this equality sign here. This is the first case. I have used the simple fact modulus property that whenever you have a modulus number, we can write this as positive x whenever x is greater than or equal to 0, negative x whenever we have x less than 0, right? So using same definition, I am writing this fact. It implies that p minus 2 plus p minus 3, which is equal to 1. Because this is positive, so we can directly take according to this rule plus x. In place of x we have p minus 2, and since it is positive, so I have taken this number positive. Okay, this is positive, so this is positive according to this rule. Okay, now we get 2p minus 5, which is equal to 1, and 2p is equal to 6, which implies p is equal to, okay. Now another case we have, when case 2, when p minus 2 is less than or equal to 0, and okay, so in this case both are negative numbers. That means we have p minus 2 negative plus p minus 3 as a negative number, which is equal to 1. Okay, so we got two values for p, namely p is equal to 2 and 3. So we observe from this p lies between 2 and 3. Okay, now let us construct x from this p. We had this earlier, we have done this. X is equal to p squared plus 1. Let us use this construction to obtain x. Okay, first I need p squared here. So we get 3 squared and 2 squared here. Okay, we obtain p squared as 2 squared, that means 4, and 3 squared, that means 9. Okay, Now we have to construct p squared plus 1, so I will add everywhere 1. So p squared plus 1 is less than or equal to 9 plus 1 and 4 plus 1. It means that p squared plus 1 lies between 5 and 10. Clear? The value of p squared plus 1 lies between 5 and 10. Okay, but what is p squared plus 1? It is x. Okay, so this is our final solution, means x lies between 5 and 10, including 5 and 10. Let's discuss this solution. We had x between 5 and 10. Okay, minimum means x minimum here equals 5 and x maximum equals 10. Okay, how many solutions are there? So we say that there are infinitely many solutions for this. Okay, now at 6 we get exactly 1, at 7 we get exactly 1, at 8 we get exactly 1, at 9 we get exactly 1, and 10 we get exactly 1. From this table we conclude that at every integral point from 5 to 10 this equation satisfies, right? And all intermediate values, decimal values, up to certain digits after decimal, we are getting a correct solution. But as soon as it is reaching up to 13th digit, we are getting deviation, observing deviation in the solution. However, accurate up to 12th digit, and this is perfectly okay.